Hey folks, just wanted to give kind of a demo and explanation of the nuclear fuel cost estimator on whatisnuclear.com and just go through some of the stuff. I kind of fixed it up recently, made it look slightly better, and so I just want to make sure you know how to use it so it can be useful for you. I think it's a cool thing. So if you go over to whatisnuclear.com and you click on reference and then click over here at the nuclear fuel cost calculator, that'll bring up the latest and greatest user interface. So there's just some settings at the top. You can like type in your tails assay and feed. These are pretty typical defaults, so maybe leave those. You then have your economic unit costs, so like cost of uranium conversion, SWUs, and these are like kind of pretty modern. These are changing rapidly, so keep an eye on them. But that's where you're gonna convert, how much fuel you need into like actual costs. And then there's a few mode settings, like given a product mass, compute feed, or other way around. And then you can also compute just like straight up fuel costs in dollars. Or you can do output fuel costs per kilowatt hour in like an equilibrium mode, which is kind of extra interesting for long-term performance. But we'll start with just this one. So the defaults here, it's like you've got your enrichment. So if you want 4% enriched and you want 1 kilogram of it, that's kind of what's calculated by default here. So it goes through and it calculates how much tails it will be, how much UF6, and then how many SWUs you need there. And you can slide the slider, and you'll see that if you go as you go up enrichment, the amount of fuel of enrichment and feed uranium goes up. So you can see that like the feed mass goes up to, you need 210 kilograms if you want to make a single kilogram of 96% enriched uranium and so on. So that's just like a basic slider, and you can type numbers in. If you want like 4.5, just type it in, or you can choose a preset. I put a few presets in here like HALEU, weapons grade, LEU, whatever. So that's like the real basics, just computing, and it is calculating like it's multiplying by the unit cost to give you these costs of feed, and then the sum down here. So for instance, you can say like, okay, if you want a kilogram of regular old LEU, here's how much it's going to cost you. It's going to be about $3,000. And then I do want to point out that these graphs, this is just showing, a graphical version of what's down here. You can make like a couple different graphs. So here's a kilogram of LEU, and you can give it a name down here. So like 1 kg LEU. And then you can click add another case, and then maybe give this one a name that's like 1 kg HALEU. So then you go up and you say, okay, I still want 1 kilogram, but I want it to be HALEU this time. And those are the only things will change. And you can see like, okay, now it's $17,000. So you've got a kilogram of LEU versus a kilogram of HALEU. Great. And you can keep going. You could add another case and say like 1 kg and you for a CANDU. In that case, you might go up here and change it to natural uranium. You still want just a kilogram, but since we're a CANDU now, you might want to go up into unit costs and say, instead of fabricating uranium oxide, let's do uranium oxide for a CANDU, which is a simpler bundle. It's a little bit cheaper. So now you have your price for CANDU. So there you go. 1 kilogram of LEU, HALEU, and natural uranium, just straight up. Now, you might say like, wow, CANDUs are so much better, but that's only part of the story. There's a lot more related to like how much burn up the reactor, how much energy the reactor can get out of a kilogram of fuel. And that's what this other mode is for, this output cost per kilowatt hour. So if we flip over to that, let me just refresh let me refresh to clear the graph down there. So we'll switch over to fuel cost per kilowatt hour, and you can see all the outputs switch to cents per kilowatt hour instead of the default. So again, let's start with a regular LWR. We'll say, let's switch it back over to LWR. And here we have like just a kilogram of fuel. But now, because we're in this equilibrium mode, you go into this reactor settings section, and you can set like the discharge burn up, which is like how much energy has come out of each fuel before you take it out of the reactor on average, and its thermal efficiency. These default to light water reactor typical numbers, so we'll just leave them there for now. So here we can say LWR with LEU. So that's cool. And then let's add another case, just like we did before. And let's switch it over to a can do. So we'll say can do, and we choose a can do burn up. They are natural uranium, so they get way less burn up. And so that's kind of how it ends up evening out. And in fact, you can see, oh, sorry, you got to change the enrichment back down. And you can see, look, they kind of like even out. So even though you're not enriching anything, you have so much more fuel to fabricate that the costs end up being, roughly the same. So there's your can do in equilibrium. Let's do like an HTGR. So we'll bring this over to triso fuel. Now, triso fuel is very expensive to fabricate. I put 7,000 as a default. That's pretty low. Like, it's really between like 10 and 20,000 at the moment. It'll probably come down, but let's just start at like 10,000 per kilogram fabrication. The burn up of a HTGR is usually, you can get like 150. That triso fuel is very robust, and if you have lots of enrichment, you can go ahead and get a lot more burn up out of that fuel. If you're high temperature, you have higher efficiency, so let's bump it up to 43. But we need HALEU, so we take it on up to, maybe we'll do 16% or something like that. So there we go. We've got all that stuff for an HTGR. And here we go. So HTGR HALEU, and you can see that, like, okay, overall it's like it's roughly as efficient with uranium. Oh, and I forgot to mention there's like how many grams of uranium are needed per megawatt hour shown in this equilibrium mode, and you can see how much waste of grams of high level waste per megawatt hour represented here when you're in this mode. So anyway, the cost is a lot higher, mostly because the fabrication cost is pretty high for triso. So you've got more SWUs, and you've got a lot more fab. So then keep going. Let's add like a SFR HALEU, something that's like not really recycling. So that's going to be similar. They can do roughly the same burn up with like a metallic fuel. You get maybe 39% enrichment, maybe 39% thermal efficiency, maybe same-ish enrichment, but the fabrication is going to be the metallic fuel, fresh HALEU. So this is not reprocessed, it's not hot fab, so it's not that expensive. And so I think that's all I need to do here, and that puts us right over here. So you can see we're, did I get the burn up right? Yeah. So here you're like, your reloads are like a little bit more than a light water reactor if you can get this like nice high. This is a pretty high average burn up actually for a fast reactor, so maybe take it down to like there or something like that. Anyway, you get the idea. And then, just for fun, let's do like a full reprocessing type thing. So if we do like multi-recycle. So this might be any kind of breeder reactor that's just taken natural uranium feed after it's started up. So let's go ahead and change the fabrication for hot fuel is expensive. I mean, it's at least this much. It's more than MOX. We'll figure it out once we get into like full equilibrium. But the burn up, since we're gonna like multi-recycle, let's crank it all the way up to like near the theoretical max of like 800 megawatt days per kilogram. We'll keep that thermal efficiency, and then let's go back down to natural uranium, because once you start the thing up with a huge amount of fissile material, you don't have to feed it anything at all. And so here you see your price goes down to nothing, and sure enough, there it is, graph down there. So that's kind of a few of the things you can do with this tool. You really can know a lot about a reactor's overall fuel cycle economics if you know the initial fuel, what's the enrichment and how many kilograms, and then if and then for like long-term performance, again, if you know the average discharge burn up, the thermal efficiency, and the feed enrichment, a huge amount about the fuel cycle economics right away without knowing basically anything else about the reactor. So very, very useful, very interesting, and I hope you find it helpful and useful. So enjoy, and send in feedback. Thanks.